Welcome to This Explainer. Today, we're unpacking a real game changer, why silicon dominates the solar industry, and how a revolutionary new plasma process is solving its absolute biggest manufacturing bottlenecks. If you've ever wondered how we're actually going to power the future on a massive global scale, well, you're in exactly the right place. Let's kick things off with this brilliant insight from MIT's Professor Donald Sadoway, which perfectly demystifies the secret to scaling up renewable energy. If you want solar cells dirt cheap, you have to make them out of dirt. Sounds almost too simple, doesn't it? But honestly, as we'll see, that fundamental truth drives the entire photovoltaics industry. Here's our roadmap for This Explainer. First, why silicon dominates solar. Second, how we build solar cells. Third, the plasma processing solution. And finally, testing the continuous method. Let's get right into it.
Section 1. Why silicon dominates solar. When we look at the relative abundance of chemical elements in the Earth's crust, silicon sits right at the very top. It is essentially rock-forming dirt. And that extreme abundance is absolutely crucial because it means silicon is one of the very few materials genuinely capable of reaching the massive terawatt scales we need for global power generation. You just can't power the globe with something rare.
Silicon basically brings an unbeatable resume to the table. Beyond being literally dirt cheap and completely non-toxic, it naturally forms this protective oxide layer that traps electrical energy super efficiently. Add in over 50 years of manufacturing momentum and a massive $50 billion global industry, well, it's pretty clear why alternative materials have such a hard time catching up. Silicon just has an incredible head start. Moving on to Section 2, how we build solar cells.
So right now, the manufacturing pipeline operates a lot like a stop-and-go traffic jam. You start by refining raw feedstock, then you move into fabricating the wafers, building the electrical cells themselves, and finally assembling the large modules. And here's the kicker. Each of these steps historically requires totally different environments, different pressures, and just a whole lot of moving parts.
And the fundamental flaw in that stop-and-go setup? Fragility. Modern silicon wafers have been scaled down to just 160 microns thick to save on material costs. That is insanely thin. Now, imagine carefully picking up and moving millions of these brittle wafers between separate wet chemical baths and vacuum chambers. You can probably guess what happens. It results in a devastatingly high rate of breakage right there on the factory floor. Which brings us to a critical question, one that engineers have literally been racing to solve. How do we redesign these factories to fix these bottlenecks, stop breaking the wafers, and, at the same time, eliminate the massive amounts of toxic chemical waste that comes from those wet baths?
That takes us to Section 3, the plasma processing solution.
Well, researchers at the Fraunhofer Institute came up with a pretty elegant solution, relying on something called atmospheric pressure plasma. Basically, this tech activates processing gases right in the open air. By doing this at normal atmospheric pressure, manufacturers can completely bypass the need for slow, batch-based vacuum systems. Plus, they can ditch those highly harmful hydrofluoric acid baths entirely. It's a huge shift. Just think about how this dramatically simplifies the whole fabrication scheme. Instead of disjointed batches where you're constantly risking a broken wafer, atmospheric plasma can handle saw damage etching, surface texturization, and edge isolation all in one smooth, continuous inline process. It's basically turning a clunky assembly line into a single, high-speed conveyor belt.
Looking at the working principles of this upgraded equipment, it's pretty fascinating. The wafers glide continuously across a heated substrate holder, getting up to 400 degrees Celsius. And while they move, these ingeniously designed purge gas curtains perfectly seal off the reaction zone from outside air and moisture. So you're getting all the benefits of a vacuum chamber without actually needing to build one. Pretty clever, right?
But it's not just for etching away material. To add the crucial anti-reflective silicon nitride coating, they use a microwave plasma reactor that cleanly showers the precursor gas onto the substrate. This showerhead configuration ensures a super uniform and effective film. And because the plasma is remote, it completely avoids contaminating the reactor walls. Just a beautifully clean and efficient design. All right, Section 4, testing the continuous method. Theoretical pipelines are great, but what happens when you actually test it? First up, the visual evidence is striking. If you compare a raw, as-cut monosilicon wafer next to one that's gone through continuous plasma etching, the difference is night and day. The process successfully strips away that microscopic damage left behind from wire sawing the silicon block. achieving dynamic etch rates of up to 7 micrometers per minute when oxygen is added to the mix. That's seriously fast. Second, for a solar cell to absorb sunlight efficiently, it can't be perfectly flat. It needs texture. The plasma expertly carves the surface with high aspect ratio nanostructures. What this does is bring the diffuse reflection down to under 10%. That guarantees the finished cell absorbs the absolute maximum amount of incoming sunlight instead of just bouncing it away. Of course, speed is everything when we're talking about scaling up. When testing high substrate velocities of 30 millimeters per second, this inline process didn't even stutter. It enabled an astonishing throughput of over 865 wafers per hour. And frankly, that is exactly the kind of continuous volume we need to meet global energy demands. But the real triumphant climax of this research, the electrical performance. The continuous plasma etched batch didn't just match the industrial reference cells made the old, slow way, it actually beat them. They saw a 1.83% relative gain in short-circuit current, so you're getting better speed, way less breakage, and a more powerful final product. Crucially, this process is also incredibly clean. In situ measurements showed that between 93 and 99.7% of the NF3 gas breaks down entirely inside the plasma. That super high utilization rate severely undercuts the toxic waste disposal costs and environmental hazard that we usually see with traditional wet chemical etching. It's a total win-win. So, as we wrap up this explainer, we are left with an incredibly exciting outlook. With atmospheric pressure plasma ready to turn fragile stop-and-go manufacturing into a smooth, high-speed continuous highway, we've essentially solved one of the industry's biggest headaches. Which begs the question, with this massive bottleneck removed, what limits truly remain in scaling our global green energy future to the terawatt level and beyond? Think about that as you consider where solar technology is headed next. Thanks for joining me on this explainer, and keep